Okay, the last two integrals we need to investigate is the integral of secant x dx, what is that equal to, and the integral of cosecant x dx. Oops. Alright, these are the two hardest of the integrations just because their u substitutions are a little bit more tricky and you have to develop the problem out yourself a little. So if we are integrating secant, we can't just do the 1 over cosine x dx and use a u substitution because we start running into problems. If we let u equal to cosine x here, then du is equal to negative sine x dx, and that's not present in the function. So we have some issues there. So the next thing we can try and do is try and go straight at it. So we can try, well, secant x has a secant in it, and I know that if u were to equal secant x, then its derivative would be secant x tangent x. So maybe I can add a factor of 1 that will help me out here to get rid of this issue that I'm having with the u substitution. So I'm going to rewrite secant x dx as the integral of secant x times tangent x over tangent x. Now, usually when I have a fraction, I let the denominator equal to my u. So, assuming this guy is my u now, then I have u equals tan x, and my du would equal secant squared x dx. Now, I'm still having an issue. I don't have secant squared. All I have is secant tangent. So, I need to make a secant squared appear somehow. So the other option I have is to multiply by more than just a tangent x. So someone developed this that was very smart. They said take secant x and multiply it by a tangent x and a secant x together, the addition of those two. Use that as your quantity for 1. And so if you do that, now letting u be the denominator, u would equal to tan x plus secant x, and du would equal to secant squared x plus secant x tan x. And notice, if you distribute the numerator here, you're going to get secant x tan x plus secant squared x, which is the exact same expression you had down there in green. Oops, I forgot the dx. But this exact same expression is showing up twice. So that's real nice and easy now. All I have to do is rewrite it in terms of what I have. So now I have the 1 over u, because I replaced that as u, and this whole expression, this whole thing in purple here, is exactly what du equals. So I can just write du here. So I have this beautiful scenario where I have 1 over u du, where I know that the antiderivative of 1 over u is ln of absolute value of u. So I'm going to end up with an integral that's ln absolute value of u plus c. And in this case, it's ln of secant x plus tan x, or tan x plus secant x. Addition doesn't matter, it's commutative. So there we go. There's our first one. And now the trick was to figure out this expression. And where did they get that from? I believe they got it from looking at u as secant x first, trying to find its derivative, but then there was a secant squared, so then they had to add on a term that looked like secant squared. But if they did that to the numerator, they also had to add it to the denominator. So they said, oh, well, look, I have two factors that are something with secant in it, so this is the same as secant x times tan x plus secant x. And then they said, well, in order to make sure that this just comes out as secant, so let's just add the secant x down there so that these two quantities, this guy here and the one on the top, will cancel out. So I think that's where it came from, but I'm not specifically sure. If you try this route over here or the route down here, you'll end up with a lot of problems. And I really don't suggest it. Just go straight for the multiplication by 1 here. Okay, so that's secant x.